Hello and welcome to EP2CM4, topic number 5. This is going to be modal analysis. Modal analysis is to deal with eigenvalue problems. So this shows up in differential equations when you have some differential operator, which might be like a sum of derivatives and constant multiples and stuff acting on some dependent variable u that you're trying to solve for, and that ends up being the same as a constant multiple of u. We're going to look at some examples of this. So d is, again, some linear set of differential operators. Lambda is some scalar, which we're going to call the eigenvalue, or maybe the mode. Finite element method solvers often have an efficient way to look for this using modal analysis. In Flex PDE, you can do this by using the keyword lambda wherever you want to find an eigenvalue, and then in the under the select keyword, specifying a number of modes. Let's say modes equal 7. Then it's going to do modal analysis for you. Okay, so it's applicable to many problems in physics, but this week we're going to focus on a few specific equations, standing waves, as solutions to the wave equation. Time-independent Schrödinger equation solutions. These are also resonant modes, so like allowed energy levels in wells, and mechanical resonance of bulk physical objects, beams. All right, let's get a little bit more specific here with standing wave solutions of the wave equation. This is the wave equation. It says that some excitation u has its second derivative in time proportional to its second derivative in space. It's Laplacian. Where the proportionality constant is the square of the speed of the wave. So that's the speed that the wave propagates on this medium. So u is some excitation of the medium. We'll look at some examples down here, but whatever the excitation is, its second derivative in time is proportional to its second derivative in space with a proportionality constant of wave speed. Let's check that the units work out. So we've got whatever units u is in, maybe it's in meters, maybe it's in joules, maybe it's in newtons per coulomb, and we've got a second derivative of this with respect to space. So this is going to divide by 2, let's say, meter units after you take 2 derivatives of this. And over here, we're dividing by 2 time units, maybe seconds. So then when you take the per meter squared that you're going to get from these derivatives and bring them up over here, you can have a meter squared per second squared, which is exactly what you'd have from the speed squared. The wave equation allows a couple of different kinds of solutions. So it allows traveling wave solutions. That is, if you substitute in something that's of the form f at, let's say, kx minus omega t, then this is the form of some traveling wave, and when you substitute this into the differential equation, as long as you have the right relationship between omega and k to give the wave speed there, then you can make this work. Actually, why don't we just go ahead and do that. So if you substitute this into the differential equation, then on the left-hand side, you'll have a second partial with respect to t. So this is, by the chain rule, we'll get f double prime at kx minus omega t times omega squared after we take the 2 derivatives of the inside of this. So this is meant to show us substituting it into that wave equation over here, which is del squared u by del t squared is equal to c of the wave squared times the grad squared of u. So when we substitute that in, left-hand side, we're going to get this. On the right-hand side, we're going to get c of the wave squared times 2 derivatives with respect to space. Since we only have x's inside, then the partials with respect to y or z, if we are even in 2 or 3 dimensions, won't do anything. They're going to give us 0. This is not a function of y or z. It doesn't change with them. So its rate of change with y or z are going to be 0. Rates of change with y or z, I should say. Next, the derivative with respect to x, it's going to work out just like derivative with respect to time did. And after taking 2 of them, you're going to have a k squared times f double prime at kx minus omega t. Okay, now we've got this same function on the left-hand side and the right-hand side, so that'll cancel. And we're left with omega squared is equal to c of the wave squared times k squared. And all right, this sort of says what the relationship between omega and k has to be so that this is going to work. Omega has to be equal to the wave speed times k. All right. Now, you might remember some stuff about how, let's say, simple harmonic motion works, and like how this wave number here, k, relates to frequency omega. Well, if we had some sort of a thing that was a sinusoidal wave, then this is going to be repeating whenever you get a 2 pi inside. So you might have a form of a sinusoidal wave that's something like a times the sine of kx minus omega t, and the k is kind of related to the spatial period of this, right? This is going to repeat every time x times k goes through 2 pi, which means that when we bring x a certain distance in the future, which is supposed to be lambda, then we've got to have kx go through 2 pi. And that specifies that k times lambda has to be equal to 2 pi for this thing to be repeating with the wavelength lambda. So that specifies that k is equal to 2 pi over lambda. On the other, we could do the same thing with omega and t, and this means omega times, well, how much time has to pass before this should repeat. That's the period, right? Just like lambda is how much space has to pass before this wave should repeat, wavelength here, how much time has to pass is the period of the wave. So this is also something that has to equal 2 pi. And that means that omega has to equal 2 pi over the period, t. All right then, what we found up here is that omega divided by k is supposed to equal the wave speed, right? But let's just check what omega over k equals in this setup, right? Omega over k would equal 2 pi over the period divided by 2 pi over the wavelength. So that's going to be equal to the wavelength over the period. And you might also know another way to write this period here, the inverse of the period is the frequency. Why is that? Well, the period is the number of seconds per cycle, while the frequency is the number of cycles per second. So they're inverses by definition then. All right, so this means we could write this as lambda times f, and this has some physical meaning as the speed of the wave, right? You might remember that this is the speed of the wave. Let's think through it again. So lambda, how much space the wave covers, I don't know that. How much space the wave covers in one cycle, yeah? The distance that it travels in one cycle, that's the wavelength. While frequency is the number of cycles the wave goes through per second. So if we've got distance per cycle multiplied by, let me write that out, distance per cycle times cycles per second, then we're going to get distance per second. Yeah? And that's the velocity. Ta-da! Okay, so what we're trying to say here, just to conclude this point, the wave equation allows traveling waves as solutions. Okay, so this is something that's allowed by the wave equation. We substituted it in and showed that it works, and this gives a relationship for one particular kind of traveling wave, which is a sinusoidal wave. Okay. That said, depending on the boundary conditions, certain frequencies are allowed to persist as standing waves, which will oscillate harmonically in time. So this is not a traveling wave, right? This is a space dependence multiplied by a time dependence. You can start this off with traveling waves by having a wave reflect and then interfere with itself going in the opposite direction. So this might happen if you've got this same wave f at kx minus omega t plus the wave going in the opposite direction, f at kx plus omega t. Adding those two things together will end up, for the right frequency anyway, giving you a standing wave. Okay, so the certain frequencies that can exist are specified by substituting this into the wave equation. So the funny thing about this one is that we didn't need to know anything about f for it to be a solution to the wave equation. Just having f be a function of kx minus omega t, I guess that's something that we know about f. We don't know what this function is, but we just know that it's a function of kx minus omega t. That makes it a solution to the wave equation as long as k and omega have the right relationship for the speed of the wave in the medium. But down here, we found out that down here we will find out, I suppose, that this different function can only satisfy the wave equation for certain values of omega. So what's required there? Well, let's substitute it in. So we substitute in this to there, just like we did up here. I mean, you can try that out. If you're a little bit confused about it, go through it. The exercise will help for sure. You substitute it in, and that's what we've done here. We've got this substitution. Two derivatives with respect to time of the cosine will give you back a cosine, but multiplied by -1 and multiplied by omega squared, again using the chain rule. And then over here, we're going to get two spatial derivatives doing nothing to the cosine, right? It's just going to be a derivative of u, whereas over here, the time derivatives ignored that u at r, yeah? So now the cosine can drop off, and we've got an ordinary differential equation for what u has to satisfy, what shape is allowed for this standing wave, dependent on the frequency. Now this is an eigenvalue problem, right? We've got that two derivatives of u ends up being equal to negative omega squared u. So this is like any differential equation, the solution to this is u, right? But it turns out that we can only find a solution for specific values of omega. So a little bit more perspective, and then we're going to dive into some examples. So you've almost made it. This Feynman lecture is the one that covers a lot of the wave stuff that we're talking about for traveling waves. So if you've never seen Feynman lectures, then you're going to want to check out the transcript of this here. Feynman was a fantastic teacher of physics that's responsible for a lot of the experiments that you had in first year physics. So he's come up with these amazingly visual and great explanation ways to show what is really going on in physics, and that's still the way that physics is taught today. So in general, solutions to this wave equation, here we've gone and written in one dimension, are traveling waves as long as k is equal to omega over cw. This is specifying that same constraint that we found there when we substituted it in. For certain frequency and boundary condition combinations, these can form standing waves. For sound, u means the displacement of the matter, or maybe the density or the pressure that's going on in this wave, and the wave speed is the rate of change of pressure with respect to density. Ooh, I've got a typo in there. This should be pressure with respect to density down there. Yeah. In an ideal gas, you can find that the wave speed is gamma kt over m. M is the mass of the atom, k the Boltzmann constant, and T is the absolute temperature, while gamma is this number called the adiabatic index, usually a little bit more than 1 depending on the gas that we're talking about. For a string, U is transverse displacement, and wave speed is the root of tension over mass per unit length. You might have seen this from first year. And in light, U is the transverse component of the electric field, or it could also be the transverse component of magnetic field, and the wave speed is the speed of light. What we're saying is that this same differential equation models all of these different physical phenomena. So all the stuff that we're doing in this unit to analyze how standing waves work to the wave equation, even if we're talking about strings or drum membranes or something, it's just as applicable to these different situations. First example, resonant frequencies and mode shapes of a drum head. Find the 5 lowest frequencies of a bass drum with a radius of 51 centimeters tuned so that the wave speed in the membrane is 1,000 meters per second. So really this is the 5 lowest frequencies of a bass drum head, not the drum itself. Bass drum itself is a little bit more complicated with like the air cavity inside participating and everything. But this will be a good introduction to what's going on in the steady state solutions to the wave equation. So to do this, we're going to be incorporating this eigenvalue problem, and rather than omega squared, you're going to want to put lambda, because that's the eigenvalue of this situation here, of this differential equation. Then build in a number of modes with modal analysis in flex PDE set up by specifying some number of modes under the select keyword and using lambda in place of the eigenvalue in your differential equation. So see if you can build that in for some circular membrane of 51 centimeters without looking at the example code, and then come back to it after you've had a chance to give that a shot. So here's our Flex PDE version 6, and we're going to build up this problem. Maybe we'll call this vid5 resonance, and we're going to stick in 2 dimensions for now. The variable we're going to need is the deformation of this membrane, which I guess we can use U. That's the one we were using up there. Select, we're going to need modal analysis. Modes equals, let's see, 5 lowest frequencies. Then under the definitions, we can put in the wave speed. CW is equal to 1,000. And for the differential equations, oh, actually, it's pretty similar to this. Div grad, yet again, of U is, instead of being 0 for a pure Laplace's equation, we're going to say that it's equal to negative lambda times U. Okay, this'll actually solve right now. We just need to go and specify what the actual, maybe it won't. We need to specify what the boundary conditions are for this setup. Yeah, so the issue is here we had load boundary conditions everywhere. If we put value of U is equal to 0, we've crashed Flex. So, by the way, maybe this is a good example actually. When this happens, you get these floating point overflows, then it can't actually terminate. So what you have to do is open up Task Manager and then go down to Flex PDE 6 and hit delete, cancel that. And after a quick video edit, you'll be right back to where you were. So we are ready now with value is equal to 0 to run it, and things worked. We've got some resonant modes. We can set a surface plot rather than a contour plot and see what the resonant modes of this drum head would be in kind of a nice visual representation here. And we can next just set up what the actual shape of this would be. So that is, rather than a square, we're going to start at, let's say 0, 0R, and then why don't I just leave that in case we want it back later. Arc, center equals 0, 0, angle equals 360, and we'll just specify what R is. R is 0.51. Okay, so there we go. There's our bass drum resonant modes. Now, what are the actual frequencies of this? Well, these are the lambdas, and lambda is supposed to equal omega squared, so we can figure out what F has to be by substituting into there. Now these actually, we didn't quite finish the differential equation, I just realized, because it should be that lambda, right, so, wait a minute here. Oh, there's a typo. You know, this definitely doesn't seem quite right. We dropped the c squared. So over here, we need cw squared is equal to del squared u. And yeah, that's in there now. So we'll have to I'll edit that back in the video. If you're watching this, you probably saw that already edited back in. Anyway, yes. So now that we've got this CW times CW squared times that, now we've got much different frequencies. So these are much higher lambda values, and we can figure out what F is by saying F is equal to the square root of lambda. Notice that at first when we typed this, lambda wasn't in red, but then after we ran the modal analysis once, it switched to a red colored kind of keyword. It gets recognized after you've run the simulation once. So this would really be omega. Omega is square root lambda. F is equal to omega over 2 times pi. Okay, now you can go report lambda, report F in the summary section here, and it'll report once for each eigenvalue that it found. You can also note that when even though we just said make one surface plot, it made all the different surface plots here. And another thing is you can put down these reports right under one of the plots rather than a summary section. And this will put the report right in the plot. So it tells you not just the lambda, but also what the F was for this plot that you're looking at there. And that's kind of neat. So we've got our resonant modes, resonant frequencies of this bass drum. You can compare the code that you made with the one that we came up with here. 750 is the first mode, and we got the same thing. All right, next one is going to be rectangular membrane waves and boundary conditions. So we're going to redo this drum situation, except instead of being a circle, we're going to make it a rectangle with a length of 50 centimeters in X and a width of 20 centimeters in Y. Now, maybe a little bit before we do this, let's talk a little bit about what we've got here. You'll notice that some of the frequencies are the same, right? So we've got the same frequency twice here, and then the same frequency twice here. Well, what's going on is that this is a degenerate resonant mode with this one. This is the same resonant mode as this one, but just rotated. You can see this a little bit better if we go back to contour instead of surface. Contour, let's make it painted a little bit better. So this is the same mode as this one. It's just rotated maybe 90 degrees. Yeah, 90 degrees from this one. And same with this. These are exactly the same modes. They're just rotated 90 degrees. Now, there's nothing special about that rotation versus another one. So frankly, I think we're kind of lucky that we didn't get more degenerate modes here. There's really like an infinite number. This would also have worked at any rotation around this. But one thing that's nice is that these two together are sufficient for you to be able to write any excitation around this as a linear combination of those two. So this is like your basis set for all of the different modes that you need, all of the different excitations. So this one and this one together are sufficient for you to write any rotation around this as a resonant mode. And that's kind of cool. Let's go back to the surface plot and then try to build in this rectangular boundary that they requested here. So maybe we'll make Lx is 0.5, Ly is 0.2, and then draw the boundary starting at 0, 0. Actually, maybe I'll not just comment. Okay, well, this comment will need to undo more than that to turn it back to a circle, but that's fine. Okay, line 2, Lx0, Lx, Ly, 0, Ly, and then close. And we've set that the value is equal to 0 before we start this. Let's just get rid of that. Yeah. Okay, so this means on all the way around this rectangle, we're going to have a pinned edge. And there we go. Okay, so we've reproduced the resonant modes if it's a rectangle pinned on the edges, and we can do even better. We can go to adding load boundary conditions on these sides. That's the next one. So imagine if we have load boundary condition on the extreme sides in Y. How are we going to do that? Well, we're going to need to separate this out. So first, let's draw the separate lines explicitly rather than saying 2 and continuing the same line. Let's just draw it as separate lines. Shouldn't change anything. All good. Next, we'll set load of u is 0. Value of u is 0. So this one is between Lx0 and Lx_Ly. Oh, you know what? This isn't right. We want to go first load of u is equal to 0. As we're along that increasing x value, that's the y equals 0 surface, and then we'll set value of u is equal to 0 on the increasing y surface. That's the far x thing. This is x equals Lx. And then on the top of it, we'll set load of u is 0 again. As we decrease x back, that's the far y surface, y equals Ly. And then we'll set value of u equals 0, a pinned boundary condition on x equals 0. Okay, so this does this sort of a setup. We've got a linear kind of mode here, like the same as if you had a pin there and a pin there, and the membrane just bounces up and down, and same thing here. And then here we've got the almost like this is like a twisting mode, you know? It's going up here on one side and then down on the other side, but it has no slope at the edge. So it still maintains this no slope boundary at this edge. It's not quite like a free surface. We're going to be dealing with that a little bit later. So this is not the thing that's satisfied by a bridge. This is a tight membrane, which is a little bit different. So these are well satisfied if the primary restoring force to equilibrium is from some tension that's applied and it's extremely thin. So this is the next almost linear string-like one. Another mode here that has to do with the width. If we make the width a lot lower, right? We make the value in y smaller, then we'll find that this mode and this mode need to happen at relatively higher frequencies, so they're not going to be in the first 5 anymore. So we can experiment with that. If we change this to 0.05, they're gone now, and we've got just these regular kind of string type modes. So these look very similar to what's going on in a string, and you might notice that the frequencies are stacked in kind of an interesting way here. Let's see if we can remember what the theory is for this. So the results are basically sine waves that go from, well, they are sine waves, right? They're sine waves. This is a full sine wave. This is 1.5. This is half a sine wave. 2, 2.5. So what has to happen for these one-dimensional modes is that we occupy an integer number of half wavelengths between 0 and L. Where am I going to write that? Okay, so maybe right here. These, that is, they have a wavelength that satisfies n lambda over 2 is equal to L. Note that here lambda is wavelength, g length, wavelength, not eigenvalue. Unfortunately, there's not enough symbols. So n lambda over 2 is equal to L, which means, I use that is a lot, I suppose. That is, again, which means n times, from what we did earlier with lambda relating wavelength and velocity to frequency, we can say that this is CW over the frequency over 2 is equal to L. And rearranging this, we can solve for the frequency. The frequency has to then equal n times the wave speed over 2 times L. So that's the theoretical frequency. In Flex PDE, you can compare this to what's going on here by maybe writing F theory, F is equal to n times CW over 2 times L. Really Lx here is the full length. And then we can report not just F, but report F theory and compare them. Whoops. Oh, yeah, N, the mode number. So you can access that in Flex by just typing the word mode. Aha. And it's pretty much exactly what we expected for this. So based on the wave speed and the length that we put in, these are scaling perfectly well. You can check that the dependence makes sense by changing CW to whatever crazy number you like, and it still matches. You can change LX to whatever crazy number you like, and oh, you know what we need to do? This isn't going to work because the it still hasn't completely halted yet. We've got a problem here. Interrupt, yes. It's crashed. What happened there is I put too much of an aspect ratio between the length in X and the length in Y. So that sort of killed the momentum of this a little bit. We're going to cancel it and come back in once. Okay, so let's try maybe 0.532. And there we go. So that's working out, still equaling with theory, and we're all good. Since these are basically one-dimensional modes, we've made the y a lot smaller to try and deal with it. You might be interested to know that Flex can actually do one-dimensional simulations using Cartesian 1 instead of Cartesian 2. So if you're ever looking for this one-dimensional mode, you can get slightly more speed and avoid those crashes like we just had by inadvertently setting a really weird aspect ratio by just switching it to Cartesian 1. So if we go Cartesian 1 here, then we can modify the differential equation to work in 1D. Because we use div_grad, we don't actually have to change anything about this. That is just going to change into derivative with respect to x and derivative with respect to x in both situations. What we'll need to change is the region drawing. So now we've only got a start value and an end value because we're in one dimension. So we'll do start 0, line 2, L. That'll draw the domain. And that, oh yeah, surface plot is not going to work anymore. Instead of that, we'll do an elevation plot. Elevation of u. Now, just like when we went into 3D and we needed to specify a cross section for a surface for a contour plot, but we don't have to do that in 2D. When we were in 2D, we needed to specify a location for an elevation plot. We would say like from 0, 0 to L 0, something like that. But we don't have to do that in 1D, right? So it's LX actually that we called it. In 1D, the elevation is just assumed over the entire range of the variable from 0 to LX. The other thing that we're going to need to do is set the boundary. So this is a boundary in one dimension is just the left endpoint and then the right endpoint. Those are the only boundaries. So we're going to specify what it is at the left end in a different way than we were previously specifying boundaries here, and that's with point. Point value u is equal to 0, and then at the other end, point value u equals 0. What this does is it says, whereas normally a value boundary condition would say, make this true until further notice. So it applies all the way across this line. A point value boundary condition says make this true right now and then go back to this not being true. Go back to the default, which is load 0. So it doesn't apply anything on the duration of this line, just at the endpoint 0, and then again at the endpoint LX. Okay, so I think that should do it. Yeah, there we go. Notice that the runtime in one dimension is so fast, that you can't even see it anymore. Right, so you just hit Control R and it's done, right? But the also the frequencies are working as well as expected, and in fact they're probably better than they were before. Yeah, I think this is closer agreement to theory than what we were seeing in 2 dimensions because it's so simple to have so many mesh elements in 1D and get a good calculation there. One follow-up on this as a challenge, can you try to work out a comparison with theory for how this should work if the right end of the structure is free? So this maybe isn't appropriate for a string, but could work for air inside a column where you've got like one fixed end and another open end, like in a lot of brass instruments. What should the waves look like now? What do they look like? How do you make it work with flex? Okay, so in this situation, you want not a full half wavelength, but half of a half wavelength. So this minus a quarter wavelength, and then a half a wavelength plus another half wavelength is the second mode. It should stop there. And the third mode will be a full wavelength plus a quarter wavelength. And this is the same stacking as this one, except instead of n half wavelengths, you need n minus a half wavelengths. So the comparison now will be, rather than mode, we're going to have mode minus 0.5 times this. And we need to modify the boundary condition. So we're going to change point value at the right end to point load. Let's see if this works. Okay. Indeed, we've got these open air column, closed air column at the other end waves stacking. And we have the frequency matching up exactly with what we predicted. So again, the wave equation is only one of a general class of eigenvalue problems that is susceptible to modal analysis. Another one is the time-independent Schrödinger equation. And the time-independent Schrödinger equation is this. It's an equation in terms of the wave function psi. So this symbol here, psi at x in one dimension here, is here on the left-hand side, we've got a differential operator. This is like negative reduced Planck constant squared over 2 times the mass of the particle, times a second derivative in space, which in 2 or 3D would become, again, the Laplacian, plus the potential energy function as a function of space, which could be as a function of location rather than just x coordinate. That operating on the wave function has to equal some constant multiple of the wave function, where the constant multiple ends up being the energy of this allowed state. So this only certain energies are allowed. This quantization idea is one of the big ideas of quantum mechanics, and that, in fact, this is where the name quantum mechanics comes from, the fact that energy is quantized here, and the allowed wave functions are quantized too. There's only certain allowed wave functions that this particle could occupy. Wave function tells you the probability that the particle exists between two given points. So if you want to know what the probability is to find the particle between x equals a and x equals b, then you take the wave function for the state that the particle's in, and you square it. Really, you multiply it by its complex conjugate to get this magnitude squared, and then you integrate between a and b, and this tells you the probability that the particle is between a and b. Something that behaves like this, where you integrate it between a and b, and that tells you the probability that this thing is between a and b, is a probability density function. A characteristic of probability density functions is that they need to be normalized for them to make any sense. So this means that the integral over all possible values of x of the PDF, oh, this should be the PDF, which is the wave function squared, is equal to 1 or 100%, because you can't have 200% probability of something happening. That doesn't make any sense. Okay, so this is another example where we should be able to apply the mechanism of modal analysis to solve for some interesting physics. Let's try out this example on the infinite potential well. So we're going to solve the time-independent Schrödinger equation for various situations of different potentials. And this is an infinite potential well from x equals 0 to x equals L, and we're going to say L is 1 nanometer, and we're going to imagine that it's an electron confined in this well. And we're going to check if the allowed wave functions and their corresponding energy match up with the theoretical values for energy that we would expect. Okay, so let's modify this code that we had before when we were dealing with strings and make it deal with wave functions. So rather than u, the independent variable, or the dependent variable, I should say, is psi. And yeah, let's find 5 modes, sure. We only have one L, and we're going to say that it is 1 nanometer. So we've got L is 1 e minus 9. We don't have a wave speed anymore. Instead of this, we are going to be specifying the Planck constant. H bar is 1.05457 e minus 34. And the mass of an electron is 9.1 e minus 31. If you don't know that offhand, you could just you could Google that. Google would be upset. Oh, sorry, this is going on YouTube. You should search on Google for that. M is 9.1 e minus 31. Yeah, and then E is lambda over, well, E is just lambda, right? E is going to be the wave function that we're going to solve here. That's the energy. We'll say negative h bar squared over 2 times m times the divergence of the grad of psi plus u times psi is equal to lambda times psi. And here's our time-independent Schrödinger equation that we've got. Okay, so this is a situation that sets up the energy is just equal to lambda. What do we need to do? We're going to start at 0. We're going to say at the left end of the well, now U is the potential energy. We should say value of psi is equal to 0. We're going to say everywhere in the well, U is equal to 0. Line to L, and then at this point value of psi is equal to 0. We're going to make an elevation plot for psi. We're going to report the energy. And then, well, reporting lambda is reporting the energy. That's That might do for now. Let's just do that. Whoops, there's some problem here. It does not allow minus in this location. Okay, so we've got to start it off. We've got to get rid of this minus h bar here at the start. So how can we deal with this? Can we put it in brackets? Yes, that'll solve it. Okay, perfect. Another thing we could have done is rewritten the differential equation so that the negative is somewhere else. Maybe we make this first term positive and put a negative in there and a negative there, and that'll solve the same differential equation. We're all good. Okay, so we've got some energies. We've got 5 different modes there. What we'd like to do is compare this with the theoretical energy. So maybe we'll make E theory, and this is equal to n squared, and that's the mode number. So we'll go mode squared times pi squared h bar squared over 2 times m times l squared. And this, we need to report it, of course. So let's report not just E, report E theory. All right, that looks pretty good. We've got some good agreement in what these energy levels of the allowed modes should be. If you're familiar much with what we should get in an infinite potential well, then these might look familiar as well. And even if you're not, you might say, hey, that's exactly the same as the modes on a string. Yes, we've essentially set up exactly the same form of equation as the wave equation here. When U is 0 inside the well, and then at the walls, the potential is infinite. At the edge of this well, when we're not between x is 0 and x equals L, the potential is so high that there's no chance that the particle could be there, and we just set the wave function equal to 0 at those points. Then we end up with a differential equation that basically says some constant times div grad of psi is equal to another constant times psi. Well, that's just the wave equation. Right, like what we were saying, what we were solving earlier was some constant times div grad of psi, or Laplacian d by dx of the variable is equal to another constant times the variable. So that was the same problem as the steady state solutions to the wave equation when we pinned both ends, and not surprisingly, we've got the same form of a solution for this infinite potential well. So the interesting physics there is in noting what is it about this time-independent Schrödinger equation that made that happen, and it's the fact that we've got the same form of a differential equation, and we also have the same boundary condition, so we should get the same shape of solution. The meaning of lambda is different. It's not this frequency thing anymore. No, lambda is the energy of this mode. A couple thoughts here. One is we're reporting the energy in units that are not very appropriate for talking about how about electron energies here. Usually electron energies are given in electron volts, which is going to be a lot easier to read than joules here. So this is joules of energy, but the joules of energy of the electron in this state of a 1 nanometer potential well is just so low that it's hard to make, it's hard to really get hard to get much meaning for this. So instead of that, let's talk about electron volts of energy. So we're going to divide this by, if we divide this by E, being the charge on the electron, 1.602 E minus 19, then we're going to convert this into the unit of energy, electron volts. Okay, so let's divide that by QE as well. What is that converted into electron volts? And what is an electron volt? Electron volt is the energy that an electron gets by moving across 1 volt of potential. So that is the kinetic energy that it gets if it goes, let's see, well, we have to watch out for the negatives here. If it moves across the potential in a direction that would increase its kinetic energy, which for an electron would be that it moves from a lower potential to a higher potential, then it gets more kinetic energy. Okay, so now we've expressed these energies in electron volts. So this is starting from 0.37 and then 1.5, 3.38, 6, and 9.41 are the energies in electron volts of these various states of the electron in this potential well. If we make the potential well wider, not just 1 nanometer, we make it, let's say, 5 nanometers, then what we expect is that the energies of the various modes goes down by a fair bit. So yes, now we've got quite a lot lower energy for the electron in this wider well. In contrast, if we make the well narrower, maybe 1 angstrom instead of a nanometer, then the energies are spaced quite a lot higher. Okay, so next thing to talk about is normalization. These wave functions are not normalized, right? It's we've only got, in this case, an angstrom of space, and yet the wave function goes up to only a little bit over 1, whereas now if we hypothetically make the well 1 meter long, the wave function still goes to about 1. Well, the integral of about 1.4 over 1 meter is much, much more than the integral of that same number over 1 nanometer. So these clearly are not normalized wave functions. They have wave functions that are normalized have to have the property that their square integrated over all space will give you 1. So how can we specify that? Well, we can make a new function, psi normed, maybe normalized or normed here to indicate that it is a normalized wave function, and we'll call this psi, we'll define this by psi divided by the integral of psi squared. Okay, so what does this do? Integral of psi squared would be, because we didn't specify a region, this is over all space then, all space that we're simulating anyway. And now we can plot this instead. So here's psi normed. It goes down to -1 and a bit. But if we take the length and make it back to 1 nanometer, then psi normed is quite a lot higher. What we'd expect is that the integral of psi normed, report psi normed integrated of this thing squared, we should get 1. Let's see. So what has gone wrong here? Psi normed is supposed to equal psi divided by the integral of psi squared over all space. Now if we integrate psi norm squared. So the next thing to talk about is normalization. These wave functions are nice, but they're not normalized, right? So if we have a height of a little more than 1, and we integrate from 0 to 1 nanometer, then it's not a thing that is going to give us a 1 overall. So that's no good. So let's fix this up and try and normalize these wave functions. We can see what the probability is right now by integrating the wave function over all space. So report, really the square of the wave function. Report integral of psi squared. And this is something that's very small, and we need to scale psi so that after we integrate it squared over all space, we've got to normalize, we have 1. So the way to do that is by taking psi and dividing it by the square root of this thing. So this thing integrated over all space is going to be nominally normalized. Report integral of psi over square root of integral of psi squared. Let's see, does this actually fit? No, this is a mess right now. But what we can do is split it into multiple things. I think I'm confusing it with the multiple integrals here. So let's first make psi normed is equal to that, and then let's try integral of psi normed. Nope, there was something that is something else that was messed up about this. I see it now. We have to not integrate the wave function, but integrate the wave function squared. These are so low because the wave function and only half of them are kind of as low because this thing is going close to 0. It's adding the positive and negative, and those are canceling a lot. So if we integrate instead psi normed, ta-da! We've got 1 for everything here. This is working out. The wave function is so large after we've divided it by this very small number, integral of psi squared, on this particular scale for the original size that we've got, that now these normalized ones are so large, and when you don't square them, you get something that's not quite big enough over this range. right? So psi normed, if we were to plot an elevation plot of that, we're going to get something that's much larger. This is E3, right? Thousands here, so tens of thousands is the magnitude of the wave function. Wave function looks like this. A lot of the time we're more concerned not with the wave function, but actually plotting the square of the wave function. And that's what looks a little bit more like this. So oftentimes you'll see these plots rather than the wave function themselves, or maybe both of them. This tells you the chance of occupancy of different spots, right? So if psi squared is what's important, then that's why you might want to plot this instead. So this is interesting. In the well, the first mode, the electron is much more likely to be found around the middle than near the edges of that well. And if it's in the second mode, then it's very unlikely to be found right in the middle, and rather quite likely to be found in either of these two locations there. Third mode has about 3 different spots that it's quite likely to be found if it's in the third mode, fourth mode 4, fifth mode 5, etc. Well, if that's all we were going to do, then we probably shouldn't bother with Flex PDE. There's a little bit more exciting things to deal with here, which is finite potential wells, ones that don't go to infinity. Now, to lead into this, first we're going to look at a different way that we could have dealt with this infinite potential well. So you might remember what we did is we actually pinned the value of psi to be 0 at the endpoints of this well. So rather than doing that, let's first shift things around. So we go from negative L over 2 to L over 2, and this just centers it at 0. We're all good here. Next thing we want to do is imagine that before we draw region 1, we've got region 0 or something, and we're going to say start negative L, negative L, line to L. Now in here, we're going to specify a potential. U is equal to 10. Not 10 electron volts, but 10 joules, which is just massive compared to the energy that the electron has inside the well. Now we're going to get rid of the load conditions here. And in here, it's going to revert back to U is equal to 0. So now what we've got is we've got a larger region from negative L to L, where the potential is 10. But then in the subset of that region, between negative L over 2 and L over 2, the middle half of it, we are going to be reverting back to the default potential of 0. So what this should do is treat the potential as nearly infinite outside of this interior region. And we'll see if we can reproduce the infinite potential well stuff. Aha. Okay. So we've still got comparison of the energies that's working perfectly. We've got the same shapes as we had before, but we're now also plotting this extra space where we're outside the well, where the energy is a lot higher. Yeah, energy much higher outside of the well here. One thing that often happens actually in quantum mechanics is that there's a plot of the energy of the well alongside with the wave function. Now these have different units, but it's helpful to see where the well is compared to this. So we're going to have to scale the well so that we can see it. If you look at these, this goes up to something like 18 or 20-ish times E8, whereas the well we said goes up to 10. So maybe we'll add into this elevation plot a plot of U times 20E. Was that E18 really? No, E8. That's what it was. Okay, 20E8 divided by 10. Yeah, so that just scales it so that the well is going to be about at the top there, and we can see now in yellow where the potential well is on this same chart to get a good picture of this. There's actually some built-in functions within Flex that can help with these with this scaling. And before we use them directly in here, let's explore them a little bit. Let's report the global max of psi normed. So this is another report value. It tells you what the biggest value of psi normed was. So psi normed has a global max over this first one. That's pretty much 0, it's saying. So that's interesting. Y is psi-normed squared, giving us essentially 0 in this situation, but 44,000 in those other situations. So it seems like it's not actually accurately plotting. Oh, you know what? Psi-normed we don't have. Let's plot psi-normed squared. So this should give us about 20,000 every time. Yeah, so 2E9 in pretty much every situation, and it seems like that is telling us what the maximum value of this thing is over the overall space. So if that's the global max of psi-normed squared, we could also do that for U, this thing that's defined, and we've given it different values in different regions, and it tells us the global max of U. Actually, it's not reporting that at all. I wonder why. Because it doesn't change with different solutions. So it's still reporting it, but it's up there. So something that in the summary section is different for different modes will be reported separately for each mode, but something that isn't is just reported up here in the usual reporting method. So global max of U is 10. Global max of psi-normed squared is this 20 and a bit E8, which means we can build in some scaling here. U times global max of psi-normed squared over global max of U will make the potential energy always sort of scaled to what's going on with psi-normed here. Yeah? So here we go. As a check, we can take the potential, and rather than 10, we can make it maybe 1, and it still scales it up. It scales it by a different quantity so that we can see it together with the wave function. We could make the length different, which is going to change the size of the well here that we're sitting in, but keep the shape fundamentally the same, and then it keeps all the scaling nice so you can see them all in the same plot. Well, the next thing that we can do now is deal with a finite potential well. So rather than making the potential effectively infinite, let's make it a lot smaller. Let's make it maybe 6 electron volts. So 6 times QE. When we have something in joules and we wanted to turn it into the number of electron volts, and then we have to divide by by QE. But now when we want to express something as electron volts, the electron volts here goes in the numerator, the QE goes there. So 6 times the charge of an electron is the potential energy that we want for the edge of this well. Okay, so we have not much different here, although the well is quite wide. So let's go back to 1e minus 9. And now some interesting stuff is going on. Aha, so look at this. The first mode is pretty similar to what was going on with the first mode before. The second mode is starting to spill out a little bit more perhaps, and then the third mode and the fourth mode is spending a fair bit of time in this classically forbidden region where the potential energy is actually higher than the energy of the mode. So this is a well which was 6 electron volts, and we've got an amount that's the electron is actually a little bit outside of this, right? So the energy of the electron is not high enough that it can go to this spot where it's got a potential energy increase that's this high. It shouldn't be able to do that because its kinetic energy is negative, yet there's some chance of finding it there. You're going to have a difficult time of measuring what its velocity was and determining that it's got negative kinetic energy if you ever catch it in that position because of the uncertainty principle. But at least what we can say is that there is some potential of finding it there, and that's kind of interesting. Now what's going on here is we have higher potential of finding it out there. Notice what's happened for the energy. The energy is now bigger than the well height. So if the energy is larger than the well height, then this electron isn't confined to the well, right? It's moving past, it's continuing on. The only reason we're able to see this mode is that we've told Flex PDE that space kind of stops at double the well width, at 1 nanometer in each direction. So in that situation, with no load at these ends, well, we can solve for something with this modal analysis, but in reality, the electron would be in this unbound state. It's moving past, and it has some perhaps resonant type phenomenon here, but then would continue on past there. So we have only 4 different bound states here for this situation. Another thing we can do is look at the energy. So the theoretical energy is a fair bit lower than, or a fair bit higher rather, than the actual energy that we have in these different modes. And it seems to get worse, like further off, as we go to these higher order modes. Given the existence of psi norm as a probability density function, we can calculate the probability that the electron is not in the well by taking an integral over just one of the regions. So let's specify over region 0. Now region 0 was everything because of the way we drew it. We drew the whole thing. So that's not going to work. The chance that it's outside the well we can't get by psi normed over region 0. But what we can do is we can say 1 minus the chance that it is in the well, which was called region 1. This is telling us the probability that, oh, something's interesting here. Okay, I figured it out. So when you say 1 here, it's not over the region that's named 1. It actually gives you over the first region, apparently. So that's kind of interesting. When you say well, then that's the thing named well. When we say 1, we don't have anything named 1, but it still works, right? And gives us the it gives us over the first region. So 1 was the region that we happen to call 0, right? And this doesn't give us over region 1 or anything. It gives us over the region 0, confusingly. If we say 2, then it does the second region, which is the well. So because of this, it's better to not name your regions 0 and 1, or they're not going to match up with this default numbering syntax. For safety, you can just give a name, maybe outside well, and then well, right? So region here, integral of psi norm squared over 2 is the entirety of inside the well. The probability that we're inside the well is very high for the low energy states, and then very low later. And really this one should be a lot lower because we should take space larger than this. If we imagine that that we take this to 10 times, I'm not sure if we can simulate that. Yeah, okay, so we made the well very narrow. Now you see the probability that we're outside the well, if we simulate more of the space, is essentially 0. But the probability of being inside the well for these other ones doesn't change that much. It doesn't matter how big the space outside the well is for those bound states. We get pretty much the same answer there. But the unbound state is really a fake answer here. This one is indicating that we need to simulate more of the space because the potential is that the chance that we're outside the well is very high. Okay, yeah, on the region stuff, if we want to know outside the well, we could just directly go, let's see, does that work? Yeah, that is working. So that gives us the same thing as 1 minus the chance that we're inside the well. Right, so it's cut off a little bit, actually a lot. It's cut off a lot, but you can see here that these are the same numbers, so you could have set this up either way. So it does work. There's just a little bit funny stuff with the region naming, and that's why you should always check that things make physical sense. All right, the third resonance topic that we're going to be talking about is beam resonance. This is maybe the most conceptually, not the most conceptually difficult, but maybe the most calculation intensive of the three resonance modes that we're going to be talking about today. A bulk 3D object satisfies differential equations that arise from applying Newton's second law to infinitesimal elements of it to equate the net force from stresses to its mass times acceleration. We're going to do that down here. But first, where does this come from? Well, if you consider a differential volume of it, then you've got forces on each side that have to do with the stress at this point multiplied by the area of that face. And you can have different kinds of stresses. You can have, this is the positive y face. So we've got stress in the y direction on the y face, Sy. And we can also have stress on the y face in the z direction, Syz, or on the y face in the x direction, Syx. So you take any of these three stresses and multiply by the area of this face, and that'll be the force on that face. Really, you should integrate, but if it's a differentially small volume, then the stress is going to be the same at all points on this face. So we don't have to consider integrating across the face. We can just multiply that by the area. The stress is not going to change that quickly. That's not quite the case for one side of this versus the other side, because there, the stress on this side, even though it's labeled as Sy dx dz, and this is Sy dx dz, and so it should cancel, and there's an equal and opposite force for every force here. They're not necessarily equal and opposite because the stress here could be different than on this side. So we are going to allow the possibility that Sy is different on this side than this side. The net force from just the Sy dx dz on each side of this would be Sy at y plus dy. Let's imagine that that's this side, minus Sy at y, that's this other side, multiplied by that area. And this thing mostly cancels. We can get rid of most of the terms here by first writing this thing as with a not one term, really two term Taylor series approximation. We'll say that it's Sy at y plus the rate of change of Sy in the y direction times dy. This is evaluated at y as well. When you take this thing, substitute it into there, subtract off this, then you have the net force on the y faces in the y direction is del Sy by del y times dx dy dz, and that's a differential volume element. So this is important. We do the same thing with the shear. So force in the y direction isn't just from the axial force on the y faces. There's a shear force from shear stresses on the x face in the y direction, Sxy, and on the z face in the y direction, Szy. So you do the same kind of a Taylor series approximation with them to get that the xy shear stresses give del Sxy by del x times this volume element as a net force, and the zy ones, zy shear stress, give del Szy by del z times the volume element as the net force on this differential volume in the y direction. So in total, the net force per unit volume in the y direction is these things added together without the differential volume element. So that's the net force in the y direction per unit volume on this unit volume of object. And this works similarly in the other directions, in x and in z. So you can say that the total force in the x direction from Newton's second law would be the total volume of, well, really the mass of this times its acceleration in the x direction. Let that u be the differential volume's displacement in the x direction, v its displacement in the y direction, and w its displacement in z. So then per unit volume, we've got that the net force vector is going to be these things in each direction. So in x, it's the x1 with respect to x plus yx with respect to y, the partial of zx with respect to z, and then that's equal to density times the acceleration in the x direction. If we also were to require that the net angular acceleration of this differential volume is finite, then we'd conclude that the shear stress is symmetric. So this requires Sxy to be Syx. You might remember this from statics, that for a macroscopic object, we can have changes in the axial y stress from one spot to another, and that allows us to apply moments on a face. But for a microscopic differential volume element here, we can't apply moments, and that means the only way to have no net torque on this thing is if the shear stresses are symmetric. So Syx has to equal Syz x, y. That is the shear stress in the x direction on the y face has to equal the shear stress on in the y direction on the x face. Okay, so now that we're in a position to believe this, or maybe remember how this thing arose in statics, we can say, well, we don't quite have a differential equation that we can totally solve yet, because this is in terms of stresses and this is in terms of displacements. So we need to relate the stresses to the displacements, and we can do that for a material in its elastic region by applying Hooke's law. So Hooke's law says that these stresses, these 6 different stresses, are related to the strains in the axial and shear form through this through a 6x6 matrix. This is using Voigt notation here. So C is the stiffness matrix. So strains multiplied by stiffness matrix will give you the stresses. And the strains themselves are defined as slopes of the displacements. So the axial strain in x is the partial in the x direction of the x displacement, whereas the yz shear strain, for instance, is del v by del z plus del w by del y. That is the slope of the y displacement v in the z direction plus the slope of the z displacement w in the y direction. This gamma is the engineering shear strain. This is the one that's nicely related through this stiffness matrix here. There's another shear strain which is called true shear strain, and that accounts for rotations. Here we're concerned only with the deformation strain. This is the one that's going to respond with stresses. Okay, the next part, now that we've related, if you were to sub all of this in, basically, so these definitions for strains in to here, and then substitute this Hooke's law relation between stress and strains into here, then you'd have a left-hand side that depends just on displacements, and a right-hand side that and their derivatives, and a right-hand side that depends on displacements, derivatives, and time. So not surprising, we're going to do the same thing that we did for the other differential equations and come up with an eigenvalue problem. We could say that this is equal to 0, and then we're solving statics problems. Instead of that, if we substitute in that the displacement as a function of position and time, so space and time, is some spatial dependence only multiplied by cos of omega t plus phi, and substitute that then by the second derivative of this giving us negative the same thing, we'll end up with the same trick as for the wave equation, where we just get the left side of this differential equation, but now only evaluated as space-dependent things, just using the amplitudes essentially, as uv and w now represent the amplitude rather than instantaneous displacement, so no time dependence, has to be equal to negative omega squared times rho times uv and w on this side. And now we've got our eigenvalue problem. Now, if you've taken EngPhys to PO4, then this might be a little bit of a review for you. Well, it hopefully is a review for you. You might remember some of these things, but it's always good to revisit it and rederive it because it's very tricky. So what we've done there, what we did there is a lot of statics problems and even some resonance type problems. So we've got this particular set of code here. We can overwrite this beautiful quantum mechanics stuff and just run this. And this is a staged problem, which will go and figure out resonant modes of this particular beam. This was a complicated multi-part beam. And we're zooming in on what is basically a resonant mode of this beam subject to different boundary conditions. So it looks like it's maybe fixed supported at one end and pin supported at the other end, and then we're getting this sort of smooth curve in, and then basically what looks like it's a pretty good resonant mode. The way we did this was by taking actually I can show you in Flex now that we got this in here, taking the differential equation that we talked about up here and incorporating this in. So what we did is define some material parameters, write in what the Young's modulus is, the Poisson's ratio, and the density, and then compute shear modulus from Young's modulus and Poisson's ratio, and get the stiffness matrix components. This is valid for an isotropic material, at least locally. We've got then the definitions of strain in terms of displacement, and then the Hooke's law stuff, the definition of stresses in terms of these strains. This is multiplying by the stiffness matrix components here. And finally, that allowed us to write out the differential equation that we see here. The derivative in the x direction of Sx plus the y derivative of Sxy plus the z derivative of Sxz is equal to negative rho times omega squared u. So we're incorporating this eigenvalue version of the problem. In the statics part of the course, we just had this is equal to 0 every time. And then in the resonance part, we said that this is equal to negative rho times omega squared times u. And then what we did is we kind of manipulated the finite element method system of solving the problem by telling it to just try a bunch of different omegas and look for where we can get the biggest displacement, and then said that's probably a resonant mode. This is abusing the idea that that this should work if we pick the right omega, and then we can get kind of a large displacement possible since we didn't incorporate any damping. So that worked out. We got some neat pictures of this. But can we do better with modal analysis? Well, let's check it out. So this, by the way, is a set of boundary conditions. We've got that it's a value of 0 in all the different directions on the bottom z surface, and then a value of, so no displacement on the bottom, and then no displacement in x and y on the top, but we are allowing displacement in z on the top z value, and that's why it can move in and out and do this sort of pin-supported thing at this end. Okay, so first off, how do we go and make this thing work in modal analysis instead of this stage problem? Well, we'll eliminate the stages. We can probably get rid of this stuff, and instead we'll say modes is equal to 5, yeah. Let's go up to one of the things we were doing before. Yeah, modes is 5. We need to set, or whatever, we need to set some eigenvalue. So we'll specify lambda somewhere rather than omega. We will say lambda and then we can determine what omega is by saying that it is equal to the square root of lambda, because that's sort of what we replaced it with. Instead of omega squared, we had lambda there, and now we should basically be good. We won't be able to draw a history plot. We just have our grid plots and elevation plot here. So let's give this a shot and see what happens. Okay, so it takes almost a minute to simulate. And the shape at the end is just a disaster. So we're gonna work on ways to clean this up a little bit, but we do find some resonant modes here. It's hard to tell which one's which by this shape because we're just magnifying these plots so much to try and zoom in on the small displacement that we had before. They are way too much for what we were anticipating, and there's some tricks that we can do to clean this up. So we're going to improve things with this next section here, constraints and quality of life improvements for beam resonance. And the things to do in here are, first of all, under select, let's say that the error limit is 0.01 because that's basically good enough. This right away will speed up the simulation quite a lot. So there we are, 7 seconds in rather than 51 seconds. Huge improvement. We'll see that the resonant modes are not exactly the same as they were before, but for what we're looking for, this is going to be pretty good. Okay, next up, what we can do is adjust these plots. Rather than plotting the x plus u times magnitude, we probably could just plot x plus u, y plus v, and z plus w. But there's something even better we could do, and that's to scale the whole thing based on the global maximum. So we'll say we want to go to 10% of what the size is in X, Y, and Z divided by what the maximum displacement was in U, V, and W. And what this is going to do is scale so that we've got an actual displacement which is always taking up about 10% of the total range that we have on the size. Yeah. So by plotting not the actual size here, but with these grid plots, x plus mt times u, y plus mt times v, and then using this global max trick, we'll get a much better scaling. So rather than just turning off the scaling like this, what we'll do is we'll just replace magnitude with this dynamic magnitude here. So there we go. Let's give this a shot. Okay, so now our resonant modes are always going to be scaled to something that we can view and see what's going on. And it seems as though we've got some twisting modes, we've got these snaking modes along the length direction, another one there. The one that we were looking for was this side-to-side bending mode, but not this this one here. The one that we had in the flex code, which originally had an omega of about 34/55, it was a little bit higher order than this. So we can report what the frequency was here, report omega by putting it right here. We can have it reported under the plot, and we're also going to increase the number of modes a little bit higher. So we'll go up to maybe 15. This might take a little while. Notice that Flex is arguably finding higher modes here. So part of what it's doing is varying around energies in order to, and values of lambda there to see what works, zoom in on things and see if it can locate any modes in between and find what really should be the first 15 modes. Okay, so even with error limit set to 0.01 rather than the default much smaller error limit, this simulation for 15 modes takes about 80 seconds, so it's quite a long time. Now, this is kind of neat though, right? Like look at all the different mode shapes that we've got here for this particular beam. All sorts of different ways that it's predicted to be able to vibrate and all that. And I think I see the one that we were anticipating before. So this is mode 14, and it looks like we don't actually see the omega reported on this anywhere. You know, I just realized I put report omega on these plots, on the elevation plots only, not on the grid plots, unfortunately. So we don't have them reported directly on here. So which one were we doing before? We had before a mode at 3455. Now is that this one? This looks sort of similar to what was going on. This is, let's see, mode number 6. So we can go down here and see what the frequency was of that. Aha, frequency 1846. So not that one. So it wasn't that one. Was it actually this mode here? So this one, mode 14. Let's check number 14. Omega 5314. So that doesn't seem like it's the right one. What about this one though? This is another mode in that resonance that seems like it's got the right order. So this one has almost one, and then not quite to the other side. This one has one. So 1, 2, 3, 4, and then over to the other side. So this one's in between there. We've got 1, 2, 3, and then we're over to the other side. So yes, mode 10. Let's have a look. And mode 10, 3462. So pretty good agreement with what we were predicting before. And this does indeed look kind of like that plot of the elevation that we had earlier before we were finding all of the modes. So this modal analysis is a great time saver if we want to find, or really kind of convenient if we want to find all the different possible funky modes that we might have for different shapes here. While there's lots more to explore with this, hopefully that's a bit of an introduction to modal analysis and how you can try to use it to solve for standing wave systems that satisfy the wave equation, solutions to the time-independent Schrödinger equation, and mechanical resonance of bulk physical objects. Thanks for watching.